Okay, so let's work on naming here. All right, first of all, backbone. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's not do 11. Let's do 10 instead. So that's going to be a decanoic acid with a branch at carbon number 2. So that's 2-methyl decanoic acid. Okay, so we have an acid salt here. So this is going to be sodium, and that's based on benzoic acid, so it's going to be benzoate. And we have 2 methyl branches at carbons 2 and 3. So that's sodium 2,3-dimethyl benzoate. Now, say this did not have say it was like that. Okay, then it would be based on a cyclohexanoic acid. And then we'd have and this is an ester. So this is the acids. Oops. This is the acid side, and this would be the alcohol side. Okay, so we named the alcohol side first. So this is going to be a isopropyl. And again, this is going to be based on benzoate. So the alcohol is going to be isopropanol. So that's isopropyl. And then the acid is a benzoate. Now, if we took away the benzene and made it just cyclohexanol, we did something very similar to this up here, so we'd have still be isopropyl. Only would be cyclohexanol 8. All right, so we've got a ketone here. And this is 1, 2, 3, 4, 5, 6, 7. And then we've got an isopropyl branch. Okay. What do we got here? This is going to be one of those fancy acids over here. And which one is it? Well, we've got 1, 2, 3, 4, 5, 6 double bonds, all cis. And that's going to make it DHA right here. Now, I didn't specify, I adjusted this one. I didn't specify which name to use. I didn't say to use IUPAC, Delta. So you could have given any of these. Now, this is a Delta. It's so that's C22 6 Delta 1, 2, 3, 4. Okay, that would be the Delta version. This is the omega end over here. So that's 3N, so that's omega 3. Any of those would work. We get another long fatty acid here. Let's see, that's okay, that's one double bond. The only one over here that has one double bond is oleic acid. Right here. So again, you can name it any of those. So we can name it any of those would work. Okay, so we've got remember drawing structures from a name. So we've got heptanoic acid, that's a 7-carbon acid. Okay, here's an acid salt, potassium. And butanate, it's 4 carbons. And on carbon number 2, is a ethyl. Here's plain old benzoic acid. And 1, 2, 3, just 1, 2. What's a wax? So it's a simple ester with a long alcohol bonded to a long acid. And it said draw a simple one. So you can draw any one you want. Okay, the simple steroid backbone. Okay, so that's okay. Heptanoate, 7 carbons. So the acid is 7 carbons long with a branch at carbon number 2 phenyl group. And then we've got the alcohol part is an ethyl. Okay, what I've done here is I have a complicated molecule. Does anyone recognize this molecule curiously? It's very addictive, based on opium. This is the part that's based on opium here. And there are 2 side chains if you start with opium, here and here. Make it into heroin, We just change those two side chains. We want to make it into any of the addictive painkillers. That's all it is. That's why heroin is so cheap. Easy to make, unfortunately. Okay, so we want to make this grayed out piece. Okay, so we're going to start with this big giant molecule. So this is going to be the alcohol part right here. Kind of a wild alcohol, but it's what it is. Okay, and so this is going to be the acid part here. Okay, it's a 3-carbon acid. So it's going to be plus 3-carbon acid. So this is the alcohol part, acid part, ester. So you just kind of bring that complicated part along with it. But it's really a quite simple reaction. So acid plus alcohol equals an ester. All that is. Okay, so we got what? We got another acid here. Excuse me, another ester. So we need an alcohol and an acid to make the ester. So which is it? Okay, so this part is going to be the that's going to be the acid part. And this is going to be the alcohol part. Okay, so let's take the alcohol part first. And here down in yellow is the acid. So we have the acid, alcohol, yields the ester.
There's alcohol, but we wrote it on the rest.
Well, actually, two OH groups, so that's what you're talking about, right? You are right. So all I did is I broke off the acid. Once you break off the acid, you have the alcohol. Which one on the left came from? The one on the right? I'll tell you. All right, and again, on these two problems, they're simple problems, just a simple ester. It's just, there's a bunch of junk hanging on the thing, but it's basically an alcohol and an acid. So find the ester functional group, then take it apart. The acid is on the carbonyl side. The alcohol is on the O side. Okay, so this question is going to be on your test Monday. Basically, we're going to look at the state, ionic state, or non-ionic state of an acid, an organic acid, at two different pHs, an acidic pH, 1 in this case, and a basic or alkaline pH. In this case, it was 9. What's the status on that acid? Okay, so let's start with heptanoic acid. Trying to find the acid. Now, an acidic situation, that OH is going to be protonated. That means that is non-ionic. In a basic situation, it pulled off that proton, leaves us with that. So this would be ionic. So basically we had something like sodium hydroxide here. That guy took this H over here and formed water.
Is that always going to be the case in an acidic environment if it's not strong enough? Pull off any like hydrogens?
The only hydrogen that's weak enough to come off is that one. All those others are very strong and covalent. I'm talking about the other H's.
So not supposed to come off.
Restate your question.
So. Is it always going to be the case that in an acidic environment that it's not going to react?
Right.
Okay.
Yeah, no react, no visible, but no react. And in an alkaline-based environment, it always comes off. It's always that one, not the other, which is, those are very, very stable H's. All of them fly like that one I'm hanging on the fluid. Like that makes sense.
Yeah.
Cool. Okay, let's label all the intermolecular forces. Well, right off the bat, all of them have London dispersion forces. So every molecule has got LDF. Okay. So this has got hydrogen bonding. So does the acid. This also has dipole. So does this. That's from this carbon to the oxygen. And this just has LDF only. And this has got dipole, no hydrogen bonding. So boiling points, the ones with the most hydrogen bonding has the highest boiling point, surface tension, and melting point, all three of those. So this is going to be, and then two of them have hydrogen bonding now, but the acid hydrogen bonding is stronger than the alcohols. So that's going to be 1, 2, 3, 4. So the octane, the alkane is going to be the weakest. The acid is going to be the strongest. Okay, so here we have a DNA molecule. Not a very long one, but so esters. Now, this does not have any carbon esters. It's got phosphorus esters. Phosphorus is an acid bonding to an alcohol. So here we've got it's one ester. That's an ester. That's an ester. So those are the esters. What is there? 4 of them. And these are the bases. Now this is a deoxyribose. You can also have a just plain old ribose, sugar. So this is a ribose sugar here. So when you're using phosphorus as the acid, they call that an inorganic ester, since we're not involving carbon. Okay, short chain fatty acids are a big deal health-wise right now. Nutritionally, they're very, very good for you. The only problem is short chain fatty acids are gaseous. So you have lots of flatulence if you got short chain fatty acids around. Do we all know what flatulence is? It's a nice name for fart. Okay, so we start with propionic acid, 3 carbons. Very, very high IMF. It's organic acid. Long chain fatty acid, so this is C3. Okay, oleic acid, olive oil. Is olive oil soluble in water? No. So it's still an acid though. Why is it not soluble in water? So we've got, that's 18. And this is the part. Okay, very, very high intermolecular forces. That piece just has LDF on it. That piece has LDF on it, but when you're greater than 7 carbons more, the LDF, because there are a bunch of them, will become strong enough to overcome the acidic end. So these guys here overcome the COOH intermolecular forces. Okay, so we have an acid and an alcohol. That makes an ester. So the backbone. So that's 1, 2, 3, 6. So whenever we have a reaction, you have to name the product and reactants. So this is going to be a 1, 2. Okay, so this is going to be the acid, alcohol, ester. So we name, with esters, we name the alcohol first, then the acid with an OH ending. Okay, so here we have an ester, alkaline environment. Esters in alkaline environments are called saponification. Yeah. What? Yes, you do. But it's fine. Because the water is kind of, Because it's an aqueous environment anyway. So an aqueous environment, you produce water, it's like one more molecule. So if you put it in, that's fine. If you leave it off, that's fine too. Good question. Okay, so we're going to saponify this ester. Okay, what's the name of this ester? Well, that's the acid end, alcohol end. Okay, so saponification means the ester comes apart. So this is a 1, 2, 3, 4, 5, and so we're going to end up with a 3-carbon alcohol. And the sodium salt of the acid. Okay. Okay, so here we have lecithin. Says, is the lecithin molecule below saponifiable? What do we look for? Exactly. If it's got an ester there, it's saponifiable. Under alkaline conditions, though, not under acidic conditions, only alkaline. Okay, so answer is yes. It's saponifiable. Why? Ester present. Is it an emulsifier? Now remember, emulsifier has got polar parts and non-polar parts. If both of those are present, it's an emulsifier or soap or surfactant. All those are same thing. Soap is the easiest one. Okay, well, that is a charge. That makes that very, very polar. Charge, very, very polar. non-polar. So we've got the attributes for an emulsifier. Okay. What's missing here? Well, we haven't an acid. Yeah,
Previous question, does it have to be a charge, or does it have to be a negative and a positive charge?
well, if you have a negative charge, you have to have something to balance. Yeah.
Multiple positives. So long as it's done.
You want a net zero charge.
But in that case, does it have to be a charge for it to be an emulsifier, or does it have to be a charge of the balance?
It has to be polar. And if it's charged, it's the most polar you can get. It doesn't have to be charged though. Because your soap you made isn't charged, but it's got a very polar part, the acidic part, and that's got that long non-polar tail. But it's not charged though. Okay, so what's going on here? What's happening to that acid? What's happening to it?
So next.
The OH became an O. Something pulled off that hydrogen, off the butanoic acid. What could do that? Remember up here? Sodium hydroxide, right. Strong base is going to pull off that. And it's going to be sodium hydroxide. So this would be like a pH 9. Yeah, pH 9 alkaline. Yeah.
Arrow, like the react. Like I understand the sodium hydroxide, but is there the additional top of this?
It's sodium hydroxide because on the right it is sodium ion there. And it's got to be a base because it took that proton off the acid. So a sodium base, sodium hydroxide. Was that?
No, I don't know, I think I was more asking like, does it like on top of the arrow for the reaction itself? You put like a positive hydrogen on there, plus heat, or does that
You
even
could do it
matter?
that way. We could have put the sodium hydroxide over the arrow as well. See it both ways.
It doesn't matter.
Either way is fine, yeah. Okay, all right, so we have a flavoring agent below. It's an ester. Two carbon alcohol. 4 carbon acid. So, going to be the 4 carbon acid plus 2 carbon alcohol. That's how you make that. So this is going to be butanoic acid. This is ethanol. A lab I used to do up at Tacoma, we would do an ester lab. And we make all this stuff. We made oil of wintergreen. Oil of wintergreen is you start with butanoic acid plus methanol. Butanoic acid smells truly awful. That's what cow patties smell because of butanoic acid. But once you make it into an ester, that acid smell totally goes away. This is no longer an acid. We made a banana flavor, all these different fragrances, really cool lab. So all the waste smelled great. All sweet smelling stuff, really cool. Okay. Now this down here is extra credit. So we've got lecithin again. And in an alkaline environment. So alkaline environments, we have esters that's going to saponify. So those will go to the acid salts. So it's going to be let's see, the acid environment, alkaline environment, sodium hydroxide. So these are going to be the sodium acid salts. So we're going to put a sodium here. Sodium here. Down here, we're going to saponify. That's an ester here. And this is an ester. So I'm going to end up, this is choline too, by the way. So we have and then we're going to have the glycerol backbone. And it's extra credit. And the last time I gave this test, no one got that. That's why it's extra credit. So yeah, I think that's the end. Of course, you'll get the flow chart. Now, there's going to be one question that's not on this practice test. I would ask you to make an ester 3 different ways. For example, let's just stop here. make that three different ways. Remember, with making esters, it can be the acid plus the alcohol. And that's a 1, 2, 3, 4, 5, 6. So that's a six carbon acid, 3 carbon alcohol. So in this case, it's going to be hexanoic acid plus 1 propanol. Plus U. Okay, that's the simplest way. Also, the least yield. The other way to make it is with the acid chloride. So this is so this would give the most yield, least yield. Then the one in the middle would be the anhydride. And the anhydride can have 2 ends or 1 end. I'm going to do it with 1 end this time. So we'll need a hexyl dihexyl anhydride. Okay, anhydrides are just dual esters. Dual esters. So this will be dihexyl anhydride, propanol again, the 1 propanol, and that'll give us that same ester up here. So a question like this, you'll see Monday as well. So that's what I wanted to cover today, this practice test. On Monday, you'll have 2 hours for further patient per year. Okay, so that's what I wanted to cover today. If you haven't got your test yet, welcome, grab it.